I will begin with a word of prayer. Once I get up here. Here we go. Dear Lord Jesus, I thank you for these students who came here, despite this being the first day of break. Help us to enjoy the math together and to get something accomplished today, Lord. In your name I pray, Lord Jesus. Amen. So let's see here. I have strong. If I have more than 50% attendance in physics this afternoon, I will be surprised. Let's see here. Did I already hit the attendance button? I just closed it, right? Yeah. Sorry if you missed your chance, but do it 1.5 times. So guys, I just posted some notes in here, and you know, they are. Well, I've got this silly machine out. Let me just show you a few things, and then I'll get back to the board. All right, come on. All right, so this doesn't quite follow the order I did things in lecture, but it's, you know, and it has some more obnoxious, like fully pedantic definitions of a parametrization, things like that. And I have some pictures in here. Like sometimes one way to picture a parametrization, I kind of drew a picture like this on the board, but you think about it as taking a line segment and then just kind of like stretching it out into the curve. You could think of it, that's what the parametrization is doing. The larger point is the parametrization is the image of the parametrizing map. So I have a few pictures like that, and I discuss oriented one way versus oriented another, talk about how formulas could be different. Here's a whole text box just answering the question, what's t? That was asked in here. I'll do these on the board. Let me not project this stuff. Here's the definition of vector, dot product, calculus. Here's some other properties of the calculus of path. Like you have fundamental theorem of calculus part 1 and 2 for vector valued functions as well. You have additivity. We proved this in class, right? We proved that in class. You also have this and that. So there are many useful rules. I don't know if any of those things matter too much to us this semester. I did have you guys prove the product rule for dot products in your homework. So that, or maybe I got to look back at the homework again. Maybe I said I'd prove it in class. If so, I'll have to come back to that. But probably not today. So we defined last time, you know, the position vector, the velocity vector, the acceleration vector. And in here I have some examples to just look at with you because I've got some nice pictures. So to start with this one, I parametrized a circle, right? So here's a circle with angular velocity omega, and I calculate the derivative of the position. I get the velocity, differentiate again, I get the acceleration. In this case, notice that the acceleration is minus the direction of the position. See, it's like the same thing, but with a minus omega squared out front. And so in terms of magnitude, you've got, it's going in a circle. This is its constant speed. Constant speed, but not constant velocity. The velocity is always changing direction. And then the acceleration is constant in magnitude as well. And it's center seeking. This is the centripetal acceleration. Let's see here. Here's another one. Mostly I just wanted to show you these pictures. So here I have the acceleration 0 minus g. I started with this formula and I differentiated to get to the top here. This example goes the other way. I start with acceleration being constant and I integrate and then integrate again to get the position as a function of time. What I've illustrated here is the motion. So like the red dotted line is the trajectory of such a particle under constant acceleration, right? So to give you a real world physical example, here. Oh, I'm sorry. That's like the third time I've ever hit a student. Yeah, you can write me up if you need to, but please don't. Sorry about that. If you want, you can you can throw it back at me. No? Okay. We always offer that to the children these days. If one has wronged another, we offer them, well, if you'd like to take your vengeance, go ahead, Let's get it over with. They punched you in the face, you punch them in the face, that kind of thing. That's right. He chopped your finger off, you chop his finger off, that kind of thing. No, it's not. Well, anyway. So this is the trajectory of constant acceleration in the vertical direction, right? And this is a parabola, right? Although it's not immediately obvious that this is a parabola, right? What are the equations? What's the equation of a parabola? You said y equals x squared. So generically speaking, y equals ax squared plus bx plus c, right? That's the equations of a parabola. Parametrically, if I wrote this out, the equations are this. X equals x naught plus v naught xt. Y equals y naught plus v naught yt minus 1/2 gt squared. Is it obvious that these are a parabola? Not really, yeah. So to prove it, what you'd have to do, right, is you could take, I guess I would just do this. I would solve the first equation for t, right, and then just plug it in down here. When you did that, you'd have something which is quadratic in x. That's a parabola. Now, a much nastier question to ask is, where's its vertex? That's easy enough to figure out in physics if we study kinematics, right? The vertex is at the zenith of the flight. It's where the y velocity is 0, right? So you could figure that out if you're... Now, that's a comment for my physics students, not for you Calculus 2 people, okay? Unless you're in Professor Dromby's class, in which case it's also a comment for you. And you should already understand what I'm saying. And if you don't, tick-tock, tick-tock, tick-tock. Let's see here. Anyway, so listen. What I've graphed here, the acceleration vector is pointing downward, right? And in blue, we have the velocity vector, right? So originally, it's going upward, right? So let me throw something less dangerous. Here, this one, right? So originally going upward, then it goes down, whee! And so the velocity is directly horizontal at the zenith of the flight, and then it's pointing up, and then as it goes back down, it points down, right? The acceleration changes the velocity to be pointing downward over time. That's what we're observing, all right? So then, as we discussed last time, well, not so much, but this is another thing. Displacement, I should define it for you. The displacement is just the change in position as a vector. So displacement is a vector. An example of displacement would be the line segment we talked about last class, right? Like PQ is the displacement from P to Q. How do we get it? Q minus P is the formula for it, right? This is the displacement from point P to point Q. We worked out the arc length, right? Arc length is synonymous with distance traveled. So you have to integrate the square root of the dx dt squared plus dy dt squared dt like this. What is this actually as it relates to velocity? See, this is the length of the velocity vector, right? That's what we're integrating. This is the speed, right? So it turns out that we can reasonably call this ds dt. It's the change in arc length per unit time. The square root of dx dc squared plus dy dt squared. So, and we don't really, I don't know how much, I need to review your homework to see whether or not I've actually even asked you a question about this, but you can define the arc length as a function of time. I have much more to say about this in Calculus 3, all right? So, let's see here. Going on. Here's a picture of circular motion where I didn't assume, in this equation, I did not assume that the input for the cosine and sine was just omega t. In the previous example, I just had omega t here, which means it had constant angular velocity of omega. This one here, I'm assuming that theta is theta naught plus omega naught t plus 1/2 alpha t squared. What that means is that this one has constant angular acceleration of alpha. and its initial angular velocity is omega naught. So when I calculate the velocity, I get this. The speed is just that. So that's r times the magnitude of omega. And then I integrate that to get the arc length, and it gives me this. So we'll probably work some examples like this in physics today, actually, but with numbers. But the larger point here for us is just this, that the acceleration has two pieces. It has the centripetal piece, and it has the tangential piece. The tangential piece is coming because there is an angular acceleration, which is non-trivial. And the centripetal piece is just because it's going in a circle. This is an inevitable consequence of particle going in a circle. It has to have a center-seeking acceleration. I think I have a homework problem where you work this out. Anyway, here's a picture. So the acceleration breaks down into two pieces, the tangential piece and the centripetal piece. And the tangential piece points in the direction of the velocity, whereas the centripetal piece points towards the center of the circle. And you can always break the acceleration of circular motion into these two pieces, all right? Now, this right here is an idle curiosity, but I'll share it with you. So I wanted an example of an interesting arc length calculation that you could not do with closed form methods. So I thought, what's more interesting than asking how far the marker travels, right? Like, what's the actual distance the marker travels, like this, right? Like, what's the actual arc length as it leaves my hand and goes to the floor? What's the length of that? If I took a string and laid it out on the parabolic path that it covers, how long is that string, right? That's a pretty natural question to ask, you know? And my thought was, when I started this calculation, that I wasn't going to be able to do the integral. So I started out. I'm like, okay, so this is the position. That's projectile motion, right? So we get, here it is in components. And then I calculate the velocity. Here's the velocity. It's the initial x is constant, velocity is constant. Then you have v naught y minus gt, right? And so I have to integrate from 0 to t1, this bad boy right here. And then, well, I thought, I'll make a u substitution. U equals v naught y minus gt, like that. I did that. And then I got this. Then I'm like, oh, I can integrate that, actually, if I make a hyperbolic sine substitution, right? And so I did. We know how to do hyperbolic sine substitutions in here, right? You're like, it's got a lot of letters in it. I know. And then that gives me a cos squared integral, which we can do like so, and then undo the substitution, and there you go. That's the formula for the arc length of a parabolic trajectory. That now I may have made a simplifying assumption, like I'm trying to remember where my starting and ending point was. I might have. See, this is what I can't remember, is like, you know, T1, where did I go to? See, I've forgotten over what extent I'm calculating the arc length here. Oh, I said right here, I made it relatively easy on myself. I started with x naught and y naught both being 0. And I said calculate the distance from time 0 to time t1 is v naught y over g. What's this time? Those of you who are in physics, what's this time? Yeah? That's the what?
Y velocity divided by gravity, so it's not necessarily negative.
Well, g is not negative. G is just 9.8 meters per second squared in these notes. But so how much time does it take if I throw this marker like this, right? Oop, to the top of the flight? How much time is that? Come on. Remember the kinematic equation? Most of you are in physics, so this isn't out of order. 0 is equal to v naught y minus gt, right? That's to the top of the flight, so the time to the top is equal to v naught y divided by g, right? So so what I'm actually calculating here, see, because I'm going to time v naught y over g, I'm calculating the distance, basically the distance from when it leaves my hand to the top of the flight. That's the formula, the meaning of it. So Anyway, I just thought I'd show that to you guys because it amused me. Oh, look, if I just go on the next page, I have a picture of what it is. it's this length, all right? Okay. Let's see here. We did this last time. I think at this point I'll put this away. I would point out, though, that I have, down here, I have some formulas which we'll probably get into today. So we talked about last time that df dx was, dy dx was dy dt over dx dt. If you calculate the second derivative, it's not just y prime prime over x prime prime. It's more complicated. It's like this. So if you're asked about second derivatives, you have to think through it. You can't just divide the second derivatives of the parameterizations. Just a warning, okay? Maybe we'll do one of those here in a minute. Let me put this away. I just want to point out that these notes are here. There's much more. There's more than I'll cover in class. They're pretty, you know, wordy. Oh, shnikes. Well, any questions about anything before I go on? Nobody? Let me work some examples then, if I can find one. Give me a second here. I have to work backwards on my phone because I don't understand how to use the gallery. If I was better at this, I wouldn't be doing this. Come on. Oh, there we go. Back to section 10.1. So some of the questions here, I'll try not to inadvertently work one of your homework problems for you. All right? That's okay? Well, I mean, come on, they're not that bad. So here, section 10.1, number 13. I'm pretty sure I didn't assign an odd problem. That's too, you know, that'd be too nice of me, right? So here you have x equals to sine of t, and you have y equals to cosecant. All right. Let's see here. Let me put down another one here. Section 10.1, number, I don't know, 16. We have x equals to the square root of t plus 1. And we have y equals to the square root of t minus 1. All right. So in both of these, we're supposed to eliminate the parameter and find the Cartesian equation of the curve. All right. And we're supposed to sketch the curve and indicate with an arrow the direction which the curve traced as the parameter increases. All right. So in this one, we're given context 0 less than t less than pi over 2, I think. Yeah. Yeah. So just to contrast this, what we did the last class is I mostly did what? I mostly just said, here's an equation, right? How would you parameterize it? I would say that's a harder problem. Here, it's a little bit easier. All we have to do is try to eliminate, our goal here is to eliminate t. If we can eliminate t, then we have found the Cartesian equation, essentially, right? What's cosecant? It's 1 over sine, right? So 1 over sine t is equal to what? It's equal to 1 over x, right? But what's cosecant equal to? It's equal to y. So therefore? And therefore y is equal to 1 over x. This is the Cartesian equation right here. Too easy, maybe. Sure, yeah, so that's a good point. The best description would also suitably restrict the boxed equation. How would that be restricted? X is not equal to 0. Let's see. 0 less than t less than pi over 2. What happens with sine? Sine goes from what? From 0 up here to 1, not inclusive, right? This is the graph of sine. What happens with the graph of cosecant? Right? I mean, it blows up at 0, doesn't it? So what are we talking about here? We're talking about, come on, 0 less than x less than 1 is how we typically limit that, right? Okay, typically we don't limit Cartesian equations, do we? Most of your mathematical life, you've just existed in a world of people would say stuff like y equals 1 over x. No strings attached, right? But this parametric equation with that domain of parameters does attach this. So thank you for asking about that. That's very helpful. So like first order answer when I ask this question is the boxed equation. The best answer also includes the inequality. All right? So let's see here. Now, and sometimes there's no, there's no domain for the parameterization given. And in that case, we can't even try the inequality part, right? At least without a lot of jibber jabber. Let's see here. So how about the second one? How do I find the Cartesian equation?
If you square the x plus 1,
Aha.
subtracted 1 to both sides, and then put t times x minus 1. Substitute that in under the y1.
So you say square both equations and then subtract them?
Yeah, sure.
I think that's, I mean, you said something different, but we're I think in the same neighborhood. So that's x squared minus y squared equals to 2. There you go. I mean, if you're just interested in the Cartesian equation, that's it. Now what if I want to find, can I write it as a graph? Like I could also do this, right? x squared is equal to t plus 1, right? Therefore, t is equal to x squared minus 1, yeah? So y equal to the square root of t minus 1 is actually equal to what? Square root of?
X squared by 2.
Yeah, x squared take away 2. Thank you. So there you go. That is, in some sense, better, right? Because it reflects the fact that y is positive, or I should say non-negative, for this parameterization, right? So what is x squared minus y squared equals to 2 anyway? It's a hyperbola, right? What are its asymptotes? So to find the asymptotes of a hyperbola, just ignore the constant and set it equal to 0. You get x squared minus y squared equals to 0. So the asymptotes of the hyperbola are just y equals plus or minus x. Like so. These are the asymptotes. That's where it goes to eventually. Now, does this hyperbola open sideways or vertically? You say sideways? How do you know? Oh, you just remember it? Oh, see, I don't do that. I have to think through it. So what I do is I try to think about, what if x equals to 0? What would happen? Where is x equal to 0? It's here, right? Think about this. If I put x equal to 0 in the equation, I get what? Minus y squared equals to 2. That has no real solutions, right? So the graph never crosses the y-axis. So you said it opened horizontally. I think you're right. Now, once I work with these a bunch, and I've done about 5 of them, I then start remembering. But then I promptly forget after the semester passes, you know? So this thing looks something like this. Right? That is the solution set to this equation. What is this actually a parameterization of? Not the whole thing, right? Yeah, just a quarter of it, I think, right? Because it, well, I mean, for this to make sense, what do we need? We need t to be greater than or equal to 1, right? That is implicit within the natural domain of these equations, right? Because if t is less than 1, you got negative square root. Yeah? So for t greater than or equal to 1, where do you start out? Y equals 2, 0, x equal to square root of 2. That's exactly this vertex right here. That's t equals to 1. And then what you're doing is you're going like this. So here's that picture that they requested. You guys can draw the graph for this one over here, right? Y equals 1 over x. So it looks like this, right? But what's the parameterization? It's just this piece, right? Which way is it going? Is it going left? Is it going down? What's going on here? You got options, right? So if you look at dy dt, what do you get? You get what? Minus cosecant? Cotangent, right? And minus cosecant cotangent, right? Listen, all 6 of the trigonometric ratios are positive when we're looking at angles which are between 0 and 90 degrees, right? So if I've got a product of 2 of the elementary trigonometric ratios, namely cosecant and cotangent, and I've got a minus out front, this is negative, right? Which says what? As t increases, y decreases, right? Or you could look at it this way. dx dt is what? Cosine t, right? What can you say about cosine t? It is positive. What's that say? That say as t increases, your x is increasing. Both of these things argue for me putting the arrow like this. Yes, sir?
We not to say that as you put in greater values of x, like if a y equals 1 over x, it gets smaller?
Well, that's also true. But this boxed equation has not anything directly to do with the parameterization. So the issue of whether or not you put, I mean, yes, if we have a function of x, we can calculate df dx. If it's positive, it's increasing. If it's negative, it's decreasing. But there, we're always, in some sense, using x as the parameter. So we're always, that's a different discussion. So parametric curves, the direction, it could go either way. So there's something to analyze. Although I don't think I need to do all of this. Like either one of these would suffice. Maybe not even this. Maybe just even thinking about the original equations. What happens when you're at t equals to 0? Where are you? Well, you're close to the origin, right? What happens when t equals to pi over 2? You're away from the origin. Okay, so it's moving left to right, Anyway. What's dy dx for this, by the way? It's apparently minus cosecant t cotangent t, yeah? Divided by cosine t. How's that work out? I have to write it out. That's minus 1 over sine t. That's cosine t over sine t, yeah? All divided by cosine t. How's that? Does that simplify? Minus 1 over sine squared t, right? Does that make sense? What is dy dx in this case? Well, it's a slope, right? But it's also, in terms of just calculus here, dy dx is what? Minus 1 over x squared. But what is x? Sine t, right? So this is literally minus 1 over x squared. See, to quote the great leader of the A-team, I love it when a plan comes together. I mean, there is like, you can go from the parametric world back to the Cartesian world and back again. These are 2 different descriptions of the same geometry. So, but you do have to be careful. Like I said, y prime prime is not the ratio of, d squared y dx squared is not the ratio of y prime prime and, well, I need to do an example. Before I do that, let me finish talking about number 16. So this, we have the parameterization here, right, of this particular piece of it. Yeah? Great. Do you want to calculate the arc length of that? I mean, I don't know if I do. First of all, it looks like it's an improper, well, no, wait a minute. Yeah, it's an improper integral. So it's, I mean, it's infinite, right? If it goes on and on, we'd have to limit it. Can you guys tell me another parameterization of this curve while we're at it? How about this? What if we put x equals to something, y equals to something else? What should I try? Cosh and sinh? All right. Which one's cosh, which is sinh? How about x is cosh, right? Cosh t, sinh t. Will that work? But what's x squared minus y squared? It's then what? It's 1, right? I want 2. So what I need to do is multiply these by square root of 2. See, if I do that, then I have x squared minus y squared equals to 2. And this makes sense for t in the reals. What our parameterization is doing now is we're getting like not just the upper quarter of it, right? This parameterization does what? It gets the whole right branch. See that? And what direction is the arrow going? Is it going down? Is it going up? What do you guys think? What's the direction of the parameterization here? Down? I guess it was 50-50, right? Try again.
Sideways.
Sideways. Oh, that is no. Let's try this out. What's dy dt? It's root 2 cosh t, right? What's that? That is greater than or equal to the square root of 2. Remember, because hyperbolic cosine is larger than or equal to 1. In other words, dy dt is positive. This curve is going up. So it's, and you know, sideways is kind of like, I don't know, like you see it's going this way here, right? But it's going that way there. So is it going sideways? I mean, you're not wrong, but you're also not right. I mean, I don't know. I mean, what if I wanted to parameterize the other side of the hyperbola? How would I get this one? Right, yeah, just put, but not for both. I mean, I guess you could do for both, but I would just tend to just flip the minus on the x and leave the y the same. I guess it depends on whether or not you want to parameterize it going up or down. If you put a minus on both formulas, then the parameterization of the left branch would be going down. If I just put a minus on the x, then we'd have a parameterization which is going up. But yeah, just basically just put a minus sign in to get the other side. All right, enough about that. So I hope that helps some of you with the early homeworks on how to eliminate a parameter. The other game to play, so both of these examples were nice in that we could kind of solve for t. That's not quite true, is it? I didn't solve for t in the first one, did I? I did what? I exploited a relation between the functions which were defining the parameterization for x and y. The other one I was actually able to just directly solve for t. Those are nice when you can do that. But you can't always do that, all right? If you see cosine and sine in your problem, probably you want to use cosine squared plus sine squared equals to 1. That's a way to eliminate the parameter. If you've got cosh and sinh in the problem, probably you want to use cosh squared minus sinh squared equals to 1 to eliminate the parameter. If you have exponentials and logarithms, you're probably going to have to use like laws of exponents and logarithms to like understand how to eliminate the parameter. But they're, you know, it's just algebra. All right, let me move on here. Oh man, I have spent entirely too long on these examples. Curses. Ah, where'd the time go? Man, rats. Well, let me do a arc length integral. And I'm not sure how this is going to go, because I just thought of this in the car on the way over here. So this might be too hard, but I think it's interesting. Listen, so in the notes I just posted you guys, there's about 4 or 5 calculations of arc length. So we did one last time, the nice one, right? The, what was it? Circle, right? So so let's see here. Reminder, we basically have this. ds squared is equal to dx squared plus dy squared in the plane, if you want to think infinitesimally. And so if we divide this by dt squared, we get ds dt squared equals dx dt squared plus dy dt squared, right? And then if you just take the square root of both sides and multiply by dt, you get this. ds is equal to the square root of x dot squared plus y dot squared dt, where I have introduced the very nice abbreviated notation x dot is dx dt and y dot equals to dy dt. So here's like a super nice way to just derive the formula for the infinitesimal arc length. All right? Why is dx squared plus dy squared? That's just basically the Pythagorean theorem, right? Like if you think about a curve, right? If you go over a little bit, you got dx here, you got dy here, and you got ds over here. And you see the distinction between the curve and the line, it goes away in the limit that dx and dy go to 0. This is a formal nonsense version of what I did with the mean value theorem yesterday. All right? So anyway, so to calculate the arc length, we integrate this, right? So one of the things that you've learned in physics, perhaps, is that you can calculate the so-called center of mass, right? How do we calculate the center of mass? Well, if we're talking about the center of mass you know, for a wire along the curve C, what we want to do is we're going to have the coordinate for the x. Well, that's going to be 1 over the mass of the curve, all right, times the integral over the curve of x dm, and y bar 1 over the mass of the curve, the integral over the curve of y dm. So let me talk a little bit more what I'm talking about here. So if this is the curve, if you go a little stretch here, right, a little ds, if we have lambda is equal to the mass per unit arc length, dm ds, then the little bit of mass here is lambda ds, right? And if the curve has uniform mass density, its mass per unit length would be what? It should be equal to the arc length of the curve divided by the total mass of the curve, whatever that is. So we know how to calculate the arc length of the curve if we have a parameterization of the curve, yeah? Um, so just to give a more specific example, let's put, x equals to t and y equals to t squared for 0 less than or equal to t less than or equal to 1. My bad. Minus 1 less than or equal to t less than or equal to 1. What is this? And let's assume it has mass 1 just to make things easier. See, if you just put the mass equal to 1, this becomes, instead of being the center of mass, it's called the center of oh, curses, I'm thinking, I've drawn I think it's called a centroid. So the centroid is just like the geometric center of something, all right? Okay, so we can draw a picture of this. This is a parabola, right? And, I did a better job from here to here, right? Where is its center? The focus? Yeah, I don't know. Maybe that's a good question. Is it at the focus? I don't know. Maybe. You might be right. I hadn't thought about that. So it's got to be somewhere here, right? Something like that. So, yeah, on the y-axis, it's got to be by symmetry here. Now, so x bar would be what? X bar would be the integral from minus 1 to 1 of x. What is x here? It's t. What's ds? For this curve right here, what's ds? ds is equal to x dot squared plus y dot squared square root times dt, all right? So how's that work out here? X dot is just 1, right? Y dot is 2t, but we square it, right? So we've got 4t squared. So to calculate the coordinate of the center of mass, or the centroid if you like, for the parabola here, we'd have this integral. Whereas to calculate for y bar, we have what? Instead of putting a t there, we put a what? Put a y, right? So we have t squared. And therein lies the difference. Although it's already clear from the geometry of the problem that this integral, the top integral, works out to what? We're looking at an odd function integrated over a symmetric interval of the origin. Any odd function, when you integrate it over a symmetric interval, 0. As it has to be from the geometry of the problem anyway, right? Because that center has to be on the y-axis by the symmetry. But what's y bar? Well, that's an integral that you can do, right? Actually, I think we can do this integral. See why? You just make like a, oh! I retract my statement. I was thinking of the tables being turned. I was thinking of the t squared being inside and the t being outside. I think we can still do it. You just make like a, this is a u. Make a u equals 1 plus 4t substitution. Then you can solve this for t, and it gives you a polynomial in u, which then you can integrate, right? You guys are going to have to tell me that integral in a second here. Come on, come back to us. That's what you guys are laughing at. It's funny. Oh, thanks, Austin. Come on, you can do it. Come on. So my point to you is that integral actually is nicer because we don't actually have to deal with the square root because you've got something multiplying in front of it. So actually calculating center of mass for a wire is an easier problem than just a straight arc length problem typically. Here's some straight arc length problems. So here's one. If I have e to the t plus e to the minus t and then y is 5 minus 2t, I calculate my x dot, I calculate y dot, I find my squared speed. I square root that thing, then I got to integrate it. So what has to happen? It's some kind of dark magic, right? There has to be some, oh look, it's a square. Ha ha ha, square root's gone. Like this is every single book problem. Every single book problem is laid on the foundation of a fortuitous event inside a square root. Like example 2, look, we did this last time. Oh, sine squared plus cosine squared has come to the rescue. The square root's gone, woohoo. You know? There's always some happy accident for these book problems. X log x. So we calculate, by the way, this is what the arc length looks like in the case of a graph. When x is equal to t, dx dt is dx dx, which is 1. So you get 1 plus dy dx squared. And so when we do this one, you get 1 plus tangent squared. Oh, happy accident. That's secant squared. Square root's gone. Yay. Every single stupid time, it's some kind of conspiracy of a square appearing inside the square root for your homework problem. All right? Except when it doesn't happen. So we haven't done this in here, but you can calculate the area of an ellipse of semi-major axis A and semi-minor axis B. The area is pi AB. It's a pretty easy calculation. It is amusing that when you do the circumference of an ellipse, it doesn't work out. So one of the last problems in chapter 11 is to calculate this with a power series solution, because that's pretty much your only method. Look, another one. Look what happened. Oh, that's right, it's a square, yay. So these are all the same in terms of the arc length problems if you're actually calculating them. And then I guess after break I'll come back and do some examples with the other things like surface area and so forth. But anyway, enough about that for today. I will shut up. Thanks guys. Have a good break.